Let's do that. Good to be here. A lot of familiar faces here. I seem to wind up here year after year, no matter what company I'm working for, including Sun at 5 years. 5 years ago, I was thinking there were really only two companies that were really aggressively working on lots of cores per chip. AMD and Intel are relative stragglers, going to 2 cores and 4 cores. One of the companies that really pioneered this, of course, is Sun with the Niagara approach. The other is ClearSpeed with 64 cores on one chip, with very, very low power. Same benefit you get with Niagara, but of course we're specifically targeting HPC. I want to talk a little bit high level about strategies for solving the heat power problem and then what ClearSpeed does to do that. I wanted to point out an interesting thing about the fact that even consumers are seeing the APC Heat issue. This is a nice, we're not going to be able to use this presentation because this is not compatible. Let's switch to the PDF. But this is a Samsung monitor that's using about 200 watts, if you see it. And down there on the bottom, you'll see a Sony PlayStation 3. That thing is using 380 watts, which is twice as much as the television. And while the Sony PlayStation people will tell you that, oh, there's a laser inside there, it's that blue laser, I looked it up, and it's a quarter watt for the laser. So I presume the rest of it is because of the fact that it's using a cell processor and a lot of bandwidth, which is very expensive and needs that cooling. Yeah. The PDF is always safe. We got it?
No, not yet.
Okay. Another thing, I remember the next slide. Have you seen what folding at home has done? They recently announced that there are 700,000 PlayStation 3s that have signed up for folding at home, and they claim that they have now gotten to a petaflop of performance, which sounds like a great accomplishment and very interesting. But if you take the fact that they're using 220 watts while running folding at home, multiplying that out, I think you'll find that the total power use is 266 megawatts. That's supposed to be a free computation, right? Because everybody's contributing their part. So that's $600,000 a day just for the electricity at consumer power rates. 2,000 barrels of oil a day for what would be a petaflop per second. This is not the best way to do folding at home. If you want to do protein folding, God, give us that much electricity and we'll give you 500 petaflops with our technology. So, thank you. First of all, the switch technology is only a fraction of the problem. We've got to look at the memory and the communication, as the previous speaker said. Slow down the clock, because we are way into the nonlinear sections of the clock where things go up as like the cube of the clock speed. Go back down and use multiple cores per control thread, but don't get so many that you can't program them. For HPC, you can easily go up to dozens of things happening at once, vector style, before you hit the limits of your programmability. Design things for 70 watts a liter because that's when you get the air cooling, no more, no less. And then think about the ISV codes adapted to this power-efficient type accelerator technology because obviously they're not embracing the accelerators yet, but it's coming. And there's some other details here I don't have a lot of time to go into. But I really like the previous speaker's point about the utilization of the cache. If you've got 21.9% utilization of the cache, that means that all of the energy that you see on like line 4 here, the blue one, 100 picojoules, very expensive. Of that, 80% is wasted. So one of the things you can do to help the strategy is, in fact, architect a chip for which all of the moves are explicit as opposed to automatic caching. HPC benefits far less from caching than standard general-purpose computing. If you're designing for TPCC, you'll have a very different approach than if you design for ANSYS, let's say, or GROMACS or Gaussian. So, at the power cost of the clock itself, I know Sun used to say in 2003 that it was about 25% of the chip power, and multi-gig says it's more like 50 to 60%. That's more recent. And Thomas Sterling of JPL said everything in the future will be 20 gigahertz in multi-cycle latency, which is ridiculous. This is like revving your engine at a stoplight. You are just waiting faster. That's all that's happening. So why waste all this energy on the clock when you could be doing more per clock? Think about the human brain. You're running at about a clock cycle of 1 second, 1 hertz, and you're using about 25 watts, and you seem to be getting a fair amount done. I don't know. It seems to be fairly effective. These cute little chips that are 20 millimeters on the side, they take like 2 liters inside of a system once you attach all these fans and power supplies and cooling and air plenum that's necessary to get everything cleared. I'm looking for a drink container because you need a gut feel for what is 2 liters. These glass water bottles we've got, like in the back, that's like half a liter. You have to have that much space inside of an air-cooled system or the temperature will just keep rising and rising. So we've got the CSX600 chip that is 10 watts, and yet it is a 40-watt chip, a 40 gigaflop chip in double precision. So you can put an awful lot of those in a given amount of space. There's what it looks like. 96 processing elements, and it does both 64-bit and 32-bit floating point. And this is not like graphics processors. These are not sloppy flops. These are the real thing. So these are IEEE 754 with all the flags and correct rounding and so on. Lots of internal bandwidth to this thing, but it's all explicitly loaded and explicitly stored. So you don't accidentally move data that you didn't mean to. And that's part of the key to the low power. Another thing is that there's only 128 million transistors. A lot of people are pushing 1 billion transistors, 2 billion, I think, on the Itanium now. But this really gets it keeps the performance up while you're only using 10 watts. There's only one control thread on here. The amount of energy used in a control thread is about 30 times that for a floating point unit. So this suggests you could, in fact, use equal amounts of power for 30 multiplier adders and for the things that's bossing them around. So that's what we do here, is we just have the old SIMD-style instruction stream with 96 of these things going at once. And the power is not that different between the control and the execution. Heat leads to bulk. This is the real issue now that I think everyone is facing. You can think of computing by the liter. How much can you pour into a given volume? This agrees with the PCI standard, the amount of you can get into a 1U server, how much power can you get into a 42 rack. They all work out to 70 watts per liter. I remember we used this in the design rules of the HPCS program when I was at Sun. So here's this little guy that's 4 inches by 6 inches that actually gets 80 gigaflops, weighs 9 ounces, uses 35 watts. The actual space this takes up is the same as its physical space. But that's not true for everything. When you look at a part that looks like it's a really interesting fast part, you have to divide its wattage by 70 and figure that's how many liters it's going to take up in a system. And there's some things like what they call GPUs, these things that are coming that may someday be 64-bit sometime in the middle of next year. They're running at 170 watts. So in fact, they're going to add a lot of bulk to the system. If you're not careful, what may seem like a really dense, powerful solution might wind up diluting the amount that you can get into a cabinet because of the heat generation. So what we've got that we're showing for the first time here at the conference is we've packed a bunch of our very low power chips into a 1U server size platform, and that's just about 1 teraflops double precision that you can rack mount and connect to a general purpose server. So you can actually get 19 teraflops into a 25 kilowatt rack. That's about 4 times the density of Blue Gene. There's a little bit of a sneak peek of what that thing looks like. And this thing is real. We've got it racked up there, about 12.7 teraflops of power on that thing. We are actually using it for molecular modeling. We've got real applications running on this thing. It's not just a stunt machine. If you were to just take the peak speed, it would be very similar to what's right about number 100 right now on the top 500 supercomputer list. And we're just wheeling around the trade show floor. Here's our old friend, Dr. Matsuoka. They recently fleshed out the entire thing and got every single one of the Galaxy 4s its own accelerator card. So that allowed them to get about 56.4 teraflops, and it's really performing for their applications. 70% of their submitted runs are Amber, and 70% of their workload total is quantum mechanical chemistry. We can now accelerate both of those things. So they finally can say that there's a real good reason to do all this stuff. I'm almost done here. I just wanted to make a remark about algorithms, and that is that we will be changing algorithms such that we use these methods that use less power. So we're actually going to see the need for low power consumption affect what software choices we make. Things like dense algorithms versus sparse algorithms. Dense algorithms are coming back. Structured grids are coming back. Things you thought were really smart in the 1970s don't seem so smart these days. So you have to re-examine what you're doing and break free of the shackles of the 20th century algorithm mindset. So that's it. Barrier petaflops and exaflops, for that matter, is the heat power problem. Transistors are cheap, but not the power that they use. So we're doing what we can to alleviate that. Heat power is not in the switching. You've got communication, you've got memory, and clock switching. Our accelerators have about 10x the power area effectiveness of general purpose CPUs because they're designed that way. And in the long term, I think application people can help just as much as the hardware designers to get around the excess power consumption. That's it. Thanks.